I'd like to talk about what angular momentum is, and I want to derive out the formula for angular momentum and the impulse and angular momentum. But first I want to go over what angular momentum is in a scalar sense. So this is the scalar formulation. So right here I have a particle P, and at this point in time it's moving along some curved path like this. I should probably make it on the path. Right now it's going to be moving this way, and it's going to have some mass times its velocity because it's moving. This mass and velocity is its linear momentum, and if this point extends forward, the perpendicular distance, so this distance right here, which is perpendicular, we'll just call it d. So what angular momentum is, angular momentum of a particle about this point O is going to be the moment of the particle's linear momentum about point O. So here's its linear momentum, and here's d. And if we use the right hand rule, x and y, we know that this is going to be what its angular momentum is. And this h sub 0, h naught, is equal to a mass times velocity times distance. So this is the scalar formulation of angular momentum. Now, if we look at more of a vector formulation, if it's in 3D, so this will be vector. We have a particle P here, and it's just moving in space somewhere. It's along this path, and right now it has a mass times velocity moving this way. And here's point O again. And right from this origin, we're going to have this position vector r. And the angular momentum h naught is going to be somewhere that's perpendicular to both of these vectors. So it's going to be this way somewhere, and it's going to something like that. We don't. It's hard to draw this, but this is going to be its angular momentum. So the angular momentum is going to be this r vector, which is position vector from point 0 to the particle's position, crossed with its mass times velocity vector. So let's look at this equation that we have for angular momentum in a little bit more detail, and let's derive out the equation for angular impulse and momentum and the equation for conservation of angular momentum. And we start with the equation we just found out for angular momentum. So this h naught, or the angular momentum, is equal to a position vector r crossed with a mass times a velocity vector. And let us take the derivative of both of these sides with respect to time. So when we take the derivative of the angular momentum, we get the derivative of the angular momentum with respect to time is going to be equal to the derivative of this cross product with respect to time. Now, in order to take a cross product with a derivative of a cross product, we need to use the product rule. And the product rule is if we have these two vectors, u and v, and we're taking a cross product of these two vectors, the derivative of this vector, this cross product with respect to time, is going to be equal to the derivative of the first vector with respect to time crossed with the first vector, the second vector, So the derivative of u with respect to time crossed with v plus u crossed with the derivative of the second vector with respect to time. So right here, we need to follow this product rule in order to take the derivative of our cross product. So when we do this, we get the derivative of the position vector with respect to time cross the mass times the velocity plus the position vector crossed with the mass times the derivative of the velocity with respect to time. And this is going to simplify a little bit, because if we look at this part of the equation right here, we have a derivative of position with respect to time. This is actually just another velocity vector. And if we have a velocity vector crossed with a mass times another velocity vector, we can use rules of a cross product, the properties of a cross product, and take the scalar, this m, outside of the cross product. So we have m of a velocity vector crossed with a velocity vector. And we know that any vector cross product with itself becomes 0. So this part of the equation right here simplifies out to 0. And we're just left with the derivative of the angular momentum with respect to time is equal to the position vector crossed with the mass times the derivative of velocity with respect to time. And this right here can also be written as the acceleration. So the derivative of the angular momentum with respect to time is equal to a position vector crossed with a mass times the acceleration. So if we have Newton's law, which is the sum of the forces, is equal to the mass times the acceleration, and we want to figure out all of the moments about this point O right here, we want to take the cross product of the position vector, and we want to do the cross product of both sides of this equation. So when we take that cross product, it's going to give us the sum of the moments about O. So now what we can do is we can substitute in that the position vector crossed with the mass times the acceleration is equal to the sum of the moments. So we have the derivative of the angular momentum with respect to time is equal to the sum of the moments about point O. Now from this equation right here, we can separate our variables and we can integrate. We bring this dt over to the other side, so we have the derivative of the angular momentum is equal to the sum of the moments about O times dt. And we want to integrate both sides of this equation. Now when we do this, we're going to integrate this from a time t2 to a time t1. And we're going to integrate this angular momentum from a final angular momentum to an initial angular momentum. And when we perform this integral, we get the following equation. We get that the final angular momentum minus the initial angular momentum is equal to the sum of this moment times dt. And right now we're just going to leave this integral as it is. We're not going to perform this integration. So we can bring this initial angular momentum to the other side of the equation. So we get the final angular momentum is equal to an initial angular momentum plus the sum of any of the moments that are acting on this. And what this is right here is the angular impulses. So the initial angular momentum plus any impulses is equal to a final angular momentum. Now, if let's say there are no impulses, this may go to 0, and we will have a final angular momentum is equal to an initial angular momentum. And this equation right here is known as the conservation of angular momentum. So with this equation, let's say we substitute in our scalar formulation, we're going to have m2 v2 d2 is equal to m1 v1 d1. And it's not uncommon to see this equation right here. So this is the initial mass times the initial velocity times the initial perpendicular distance is equal to a final mass times a final velocity times the final perpendicular distance. So this equation right here is valid if there are no angular impulses acting on the system. If there's a moment or some angular impulse that's acting on the system, it needs to be accounted for, and it's accounted for in this term in the equation right here.